Let's explain how backbone persistence works. To do so, we've created a demo of a very simple game. We control a character who can move and jump around the scene. We can collect a few coins and see how they accumulate in the counter. If we try to open the door to level 2, we're told that we need the red key. But it's out of reach. To get to it, we activate a nearby lever. When we do, a platform begins to move, allowing us to reach the top of the columns. We jump, collect a few more coins, and finally reach the red key. Now we can open the door and move on to Scene 2. Upon entering Level 2, we find a similar scene with levers and columns that help us reach a yellow key and open the door leading to the end of the game. But let's take a closer look at the coin counter and the red key we had. When transitioning between scenes, we've lost all the coins we had collected as well as the red key. What's more, if we go back to Level 1, all the coins have respawned and the scene has reset to its original state. This isn't the behavior we want. The game works, but it lacks persistence. Each scene resets when it loads. We need to implement something that maintains the game state across scenes. This is where backbone persistence comes in, offering a simple yet powerful set of tools that give game developers everything they need to save and load the game state at any point. The first step in any scene is to add a persistence manager. Create an empty game object, name it however you like, and add the persistence manager component. This object is essential. It handles all loading and saving operations at runtime. Without it, persistence simply won't work. The next step is to identify which elements of the game should be persistent and which do not need to be saved. To make the persistence system more efficient, we'll distinguish between two types of persistent elements. Game-persistent elements are those that must be present throughout the entire game regardless of the current scene, such as the number of coins or the keys collected. On the other hand, scene-persistent elements are those that only need to be loaded within the current scene, like the 3D objects that represent the coins and keys, since we don't want the player to be able to collect them again upon returning to the scene. Finally, there are elements that we don't want to persist at all, such as the state of the lever and the platform. These can reset every time the scene is loaded. Some elements can be persisted automatically, like the 3D objects representing coins and keys, simply by using components provided by Backbone, such as PersistentObjectState or HierarchyPersistence. This way, their active state is remembered automatically between scene loads. But other elements, like the UI counter showing how many coins we've collected, or whether a door should start opened or closed, need a bit more manual control. In these cases, we define custom serializable attributes or data classes, marked with GamePersistent or ScenePersistent tags, and use dedicated scripts, like a Scene Manager or Game Manager, to apply their values at runtime. This separation between automatic and scripted persistence gives us both simplicity for common cases and full flexibility when we need to control complex logic. Now that we've explained the core concepts of backbone persistence, let's move on to implementation. Let's make the coins and keys persistent, so once collected, they won't come back when reloading the scene. There are two ways to do it with Backbone. First way is adding the PersistentObjectState component to each coin and key. That's enough for Backbone to remember if they were active or not. Second way is appropriate if we have many objects, then it's easier to group them under a single parent and add a HierarchyPersistence component to that parent. It will automatically track the active state of all children. Both HierarchyPersistence and PersistentObjectState rely on the object's full hierarchy path as a unique key for saving and loading. That means every game object involved in persistence must have a unique path under its parent. No duplicate names at the same level. You must not rename or move those objects in the hierarchy after saving. If the path changes or is duplicated, the system won't be able to match the saved data to the right object, and things might not load correctly. Now, let's talk about elements that can't be persisted automatically, like the UI coin counter or the state of complex objects like doors. For the coin and key counters, we need to store the values manually. These are not physical objects in the scene, but variables that reflect the player's progress. For that, we use GamePersistent fields. They persist across scenes and are perfect for global values like the number of coins or collected keys. To reflect those values in the UI, like updating the coin counter or showing collected keys, you're expected to implement a custom game manager script as part of your own game logic. This script is responsible for syncing the saved data with the UI and any gameplay systems when the game loads. It's a clean and centralized way to handle global state and ensures consistency across scenes without duplicating code. Your game manager should also implement the ISavable and ILoadable interfaces so it can properly react to save and load events, updating values, refreshing the UI, or initializing systems when the game state changes. As for doors, it's not enough to save their position or rotation. Doors have internal logic, animations, locks, and specific conditions to open or close. That's why we store their state in simple scene-level variables, like door 1 open, and mark them with the ScenePersistent attribute. Then, during scene load, a custom scene manager script, which you implement as part of your own game logic, reads those values and opens or closes the doors accordingly. This script should implement the ILoadable and ISavable interfaces to properly respond to save and load events, giving you full control over how interactive objects behave after loading. While you could technically place GamePersistent and ScenePersistent fields directly inside your Game Manager and Scene Manager scripts, a better practice is to separate data from logic. In this example, we've followed that approach by creating dedicated serializable classes for storing persistent data and separate manager scripts to handle behavior. This makes the codebase cleaner, easier to maintain, and more scalable, especially in larger projects. Once you've created your Game Manager and Scene Manager scripts and assigned the appropriate persistent data classes, the next step is to place these managers in your scenes. Simply add them as components to game objects in the scene. One for global management, usually marked with "Don't Destroy on Load," and one for each individual scene. With everything in place, the only thing left is to call save and load at the right moments. In this example, we'll trigger load when entering the scene and save just before leaving it. This ensures that all data is properly restored and stored between scenes or play sessions. The best moment to trigger a save is right before calling Scene Manager Load Scene, ensuring that all current data is written before transitioning away. For loading, the recommended approach is to perform a delayed load call inside the start method of each scene manager, using a coroutine that waits one frame before executing. This guarantees that all scene objects are fully initialized and ready to be updated with persistent data when the load operation occurs. Now, let's see the persistent system in action. We start in level 1. We collect a few coins and grab the red key, then use it to open the door. Now we enter Level 2. Notice how the UI still shows the correct number of collected coins, and the red key is still in the inventory. That's because this data is stored globally using GamePersistent. In Level 2, we collect more coins and the yellow key. We will use the key to open the final door, but instead of continuing forward, we go back to Level 1. Everything is still working as expected. The UI counters reflect all the coins we've collected so far, and both keys are in the inventory. However, the coins and the red key objects we already picked up in Level 1 are no longer there, because their individual states were saved using ScenePersistent. This gives us a fully working, scene-aware persistence system. Global state is shared across scenes, while each level retains its own local state independently. By the way, all the code, animations, and demo scene elements you see here are included with the asset, ready for you to use, modify, or integrate directly into your own games, however you like. For more information, make sure to check out the online documentation. You'll find a complete reference guide with usage patterns, detailed examples, and best practices. It also includes a full section on enum arrays, a powerful programming tool that will help you keep your game's codebase clean, scalable, and easy to maintain, no matter how big your project gets.